Well, welcome to week 5 of case studies in scientific literacy. So for the next 4 weeks, we are going to be talking about climate change. And my name is Shirley Baker. I'm in the School of Forest Resources and Conservation in the Fisheries and Aquatic Sciences program. And my research has really focused on clam aquaculture and sea urchin health and ecosystem services, so marine kind of stuff. But kind of woven throughout my research has been environmental change and more recently climate change. I teach a class called Marine Adaptations, which is really fun. And I also teach a graduate level class on natural resources in a changing climate. So if you need to contact me, here's my contact information, email, phone, but probably the best way is on the Canvas inbox, maybe. So here I am with my 3 boys who are now bigger than me. Okay, so we are going to be talking about climate change. We will talk about, is climate changing? What is causing climate change? How do we know that it's us? And what does the future hold? What are future projections? And how confident are we in those projections? And then at the end, in the 4th week of this section, we'll talk about what are some of the sort of economic and social implications of climate change? So we've all heard statistics that like 1 in 4 Americans is skeptical of climate change. And this is just a graph showing basically that there's still a lot of people that disagree that humans, for example, are the cause of climate change. There's a lot of people that just don't know. And there's some people that would agree with that statement. And in fact, John Oliver, on Last Week Tonight, my graduate student sent this to me, quoted those statistics that 1 in 4 Americans is skeptical of climate change. So I'd encourage you to go watch this. We're not going to watch it now because it's several minutes long. But he basically said that asking if you believe climate change is real is kind of like asking what's the bigger number, 5 or 15, or are there owls? It's kind of like, well, duh. And so I would encourage you to go to these websites and take a quiz about your own knowledge and attitudes about climate change. So this one, what's your climate profile? It's not really, are you skeptical of climate change? It's more like how alarmed you are about it. Are you really alarmed about climate change, or are you just kind of like, whatever? And I have to say that the first time I took this, I was actually kind of surprised where I fell out on that continuum. And then after I'd taught natural resources in a changing climate a few times, I actually became more alarmed. I don't know what that means. And then here's a NASA quiz about your climate change knowledge and an EPA quiz about your climate change knowledge. So it's kind of interesting to take these and see where you kind of fall out on your attitudes and knowledge of climate change. And hopefully, by the end of the next 4 weeks, you'll know more, right? So John Oliver, said these statistics about 1 in 4 Americans is skeptical of climate change, and went on to say that if we look at what scientists think, 97% of them endorse the position that people are causing climate change or global warming. And he also pointed out that in debates that we see in the media, usually it's one climate denier and Bill Nye the Science Guy or somebody. So it's always like 50-50, right? But in reality, because 97% of scientists are saying, yes, it's real, we should be having debates like this, right? A whole room full of scientists and 2 or 3 deniers, right? But what is all this evidence that these scientists are all excited about? How do we know, or what is changing about climate? So, today we're going to talk about what about climate is changing. We're not going to get to what is causing that or the proof that humans are causing that. We're just going to talk about what is changing. And I actually don't like the term climate change because there's a lot of things that are changing that aren't necessarily climate. So I really like to just call it global change, but we'll call it global climate change, and sometimes I shorten it to GCC because that gets really long on the slides after a while. Okay, so we're going to talk today, and we may not get through it all today. What is changing? Primarily, we're going to be talking about what is changing, as well as some of the symptoms of this change. So, there are a lot of different lines of evidence that things are changing. The world is changing. Temperature rise, warming oceans, a lot of things having to do with ice, sea level rise, extreme events, extreme weather events, ocean acidification. So we're going to talk about some of these. We may not get to all of them today. Okay, we'll start with temperature rise. So I just pulled this one. Somebody posted this to Facebook. It's kind of a cartoon of temperature in the last 22,000 years before present. So 22,000 years ago, the Earth global temperature was colder than it is now. And it gradually, you can go to this website and see the whole graph. It's really, really long, so I cut it off. And it gradually rises, blah, 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 all the way to, the Industrial Revolution. And then we see that, whoa, it starts to get faster and faster and faster increases until the present day, that's like increasing really fast. And then they put some projections in here, which we'll talk about in week 3 or 4. Okay, but this is a cartoon. Let's look at some other data. So starting back, really long time ago, 54 million years to present day. And okay, we don't know the temperature that the Earth was 500 million years ago, right? But we can use oxygen isotopes, and in week 2 or 3, we'll talk about how those are used. But for now, let's just believe that oxygen isotopes are an indicator of temperature. So we see that sometimes in the past, the Earth was hot, and sometimes it was cold. So one of the important things we see in this graph is that Earth's temperature is dynamic. It's not flatlined. It changes. The other thing that we see is that actually Earth has been warmer than it is right now. We're actually in maybe a little cold period compared to what it has been millions of years ago. Okay, now we're going to take a more recent little chunk of this up to about 60,000 or 60 million years ago. And we're going to look at that. So now what do we see? So if you guys had microphones, I would ask you to answer. But we will just So one of the things we see is that in the last 2 million years, we've had some really rapid cycles of temperature going up and down, up and down, up and down. Okay, that's interesting. So now let's take an even more recent chunk of this graph and look at, oh, and now this graph flipped. So now we have 400,000 years ago over here and present over here. I've got some other stuff on here that we'll talk about next week. So let's look at temperature right now. So now we see that in the last, say, 11,000 years, the Earth's temperature has been relatively warm. And, you know, there's blips, but it's compared to here, it's been relatively stable. And if we go even more recent, so 1880 to 2013 temperatures, we see that temperature has increased 1 degree between about 1905 and 2005. That seems like a lot. And here's some figures showing change in temperature from 1885 to 2014. This is actually, I don't think I put the website on here, but it's, you can go to the website and it'll actually show it. You can scroll through the years and the temperature changes. It's really cool. So temperature change compared to an average between 1951 and 1980 average. So one of the things we see is that the last 20 years or so, this change has been accelerating. So it's changing, getting hotter rapidly, and that the greatest change has actually been in the Arctic. And next week we'll talk about why that might be. But the Arctic has, the temperature increase has been pretty high. And I think in some little newsletter thing I get online from UF, there was a link to some vegetable growers newsletter that had a link that August 2016 was the hottest in 136 years. And again, this is like a, you can go to the link and it'll show the years scrolling by. Okay, so temperatures seem to be getting warmer, right? Okay, we've got several lines of evidence that recently global temperature has increased. How about the oceans? Are they also increasing in temperature? So here's where we actually have less data on the oceans, just because people haven't been exploring them. We can use isotope data like we did in the previous slides, but I just wanted to mention that now there are almost 4,000 of these floats. Since I'm a marine scientist, I'm interested in this. There are about 4,000 of these floats around the world that are going up and down, up and down, up and down, measuring the temperature of the ocean down to about 2,000 meters, which is really cool. Then they pop up, they send their data to a satellite, and it goes to some computer somewhere. Anyway, kind of cool. So if we look at heat content of the ocean, so this isn't temperature necessarily, it's a calculated heat content of the whole ocean. Again, we see that heat content of the oceans appears to be increasing. And in fact, in the top 700 meters or so of the ocean, It's increased about 0.3 degrees Fahrenheit since 1969. So 72% of the Earth is covered by water. And we often think of really deep oceans, and there must be like a lot of water, right? And there is a lot of water. There's 1.3 billion cubic kilometers of water. But if we sucked all the Earth's oceans dry and balled them up into a little ball, that's how big it would be, which I find really interesting, because we have this kind of perception that the Earth's oceans are just vast and like a huge thing, but it's really just the skin on our globe, right? But it's still a lot of water. But all that heat, because of the high heat capacity of water, all that heat is going into this little ball of water and heating it up. So here's another way to look at heat content over time. So from 1960 to 2000 whatever, of land and ice and atmosphere, of deeper ocean down to 2,000 meters, and more surface ocean down to 700 meters. So what do we see in this figure? We see that a lot of heat is being absorbed by the oceans, not by the atmosphere, not by land, not by ice, by the oceans. And that's primarily because, again, of the heat capacity of water, which is way higher than that of the atmosphere. So our oceans are warming up. So we have global temperature rise, we have warming oceans sucking up a lot of heat. We also have decreased ice things, including shrinking ice sheets. So ice sheets. Keep in mind that ice sheets is ice that is on some land mass. So next we're going to talk about sea ice, which is different, and glaciers, which are different. This is ice that is on a land mass. So this is Greenland, in case you didn't recognize it. And these indicate the melt extent. So during the summer, these ice sheets typically melt back some, right? So in 1992, these pink areas are how much smaller the ice sheet got. 2002, the ice sheet got quite a bit smaller. And then in 2012, whoa, there's not a lot of ice sheet left in their summer. But then, 2013, not as much melted. It's still more than 2002, but not as much. So that's interesting. So ice sheet melting is dynamic. It changes over time. Another way to look at it is the mass of that ice. So NASA can measure ice thickness using very satellite data. And so this is ice mass in billions of metric tons, change over time since 2002. So the ice mass has been changing at about 290 billion metric tons per year. That's a lot of ice. This is an article by Rolling Stone, of all people. Yes?
Was that globally or just for Iceland?
This is just for Greenland. Yeah. So here's an interesting article in Rolling Stone about a glaciologist, somebody who's studying the ice sheets of Greenland. And he has some interesting theories, but one of the things that happens is that once you get some melt, then that water is kind of sitting on the ice sheet as a lake. And it's darker than the rest of the ice. So it absorbs even more heat from the sun, right? Darker things absorb more sun, which we're going to talk about next week. And then we get these rivers that will suddenly disappear into the ice sheet and go under the ice sheet, between the ice sheet and the ground, in Greenland, kind of forming a lubricant that makes the ice sheet move kind of out into the ocean, which we'll also talk about. Very interesting. So you can go to this article and watch a little video about this guy, Jason Box, who studies Greenland ice sheets. So we talked about there's a lot of extra heat in the Arctic, and that is contributing to the loss of these ice sheets, for example, on Greenland. The Antarctic ice mass at the opposite pole is also changing. And again, this is NASA satellite data. So, and ice mass in billions of metric tons. So it's not as fast as loss of Greenland ice sheets, but Antarctica is also losing mass. So 134 billion metric tons of ice per year. I just can't even imagine how much that is. Okay, so we've got shrinking ice sheets. We've also got declining sea ice, which is different. Okay, we've all seen this picture, right? The polar bear on the little piece of ice. We don't know the story behind this. It's used in the media because we're like, oh, a polar bear. But if we look at sea ice, so now sea ice is ice that is not on a continent, not on land. It is floating over the water. So if we look at the September extent of sea ice, so that's the lowest extent it's going to be over the whole year, right? Because it's melted in the northern hemisphere. It's melted all summer, and it hasn't started to freeze up again. So September is the lowest amount that you're going to have all year. And again, if this is satellite data, and here we have millions of square miles of sea ice. So one thing we see is that it's changing. We're losing about 13% of our sea ice, Arctic sea ice, per year. And it also seems to be, it's variable, and it also seems to be increasing. The rate of loss seems to be increasing. So 2012 was the lowest extent on record. And then remember that figure of Greenland ice sheet had more ice in 2013 than 2012. Well, sea ice was the same. And again, that loss seems to be accelerating. Here's another way of looking at the Arctic sea ice from 1979 to 2014. And again, this is, I didn't put the website, but again, it's a little slidey thing where you can slide along and choose whatever year you want, or you can let it play and go through. So in 1979, the September extent, there was always sea ice all the way up here, and then 2014, the sea ice there was always open ocean. Okay, so this is a really cool little video of, am I going to do it? Yes. There's no sound, so. So the lighter color represents older ice, and this is just going to go through the years. It looks like a stomach or something. I don't know. But you'll see that by the time we get to closer to present day, there's a lot less Arctic sea ice. Okay. So loss of sea ice is also occurring on the other pole. So, whoops. So here we have Antarctica. A famous sea ice area is called Wilkins Ice Bridge. And here I have a series of pictures. So this is sea ice and then open ocean. So this is the February and March which is the end of the Antarctic summer. So between February and March, we can see that it was solid sea ice out to this line, and now it's solid sea ice only to here. So now this is just kind of floating chunks of ice. It's not a solid ice sheet or sea ice. So then we have more breakup of that ice sheet, and by late November, we've just got this bridge of solid ice, and the rest is just kind of ice chunks. And then in April 2009, that ice bridge that has always been there for as long as people have been monitoring it, it's gone. So this ice bridge that has just always been there, a sheet of sea ice, is now gone, and it has not reformed since 2009. Okay, so we've got shrinking ice sheets, we've got declining sea ice. How about glaciers? Something that maybe we've actually seen. I've never actually been to Greenland, so I haven't seen ice sheets. I haven't been to the Arctic, so I haven't seen sea ice. But I have been to our national parks, and I have seen glaciers. So how about those? So a glacier is always moving down a mountain, right? But when the forward edge is melting faster than it's moving, then it appears to be kind of moving backwards. So it's that whole front edge is kind of shrinking back. And looking at several different glaciers around the world, they have lost about 400 billion tons of ice per year since 1994. So again, that's a lot of water. Hard to imagine. So USGS and the National Park Service has been doing this really cool thing because people have been going to parks, right, and taking pictures of glaciers. We have documentation of their retreat. So you can go to this website, and they've got photographs through the years of different glaciers. So it's really, really cool. So for example, here's this glacier, Grinnell Glacier, 1940 and 2005. It's a lot smaller. So stop me when I'm like getting close to the end of class, because I'll have no idea. So some glaciers have lost like a third of their size since 1850. And of 150 glaciers that were documented in 1850, only about 26 of those exist, which is amazing. So here's a list of some glaciers that by looking at these photographs, they're able to calculate the area, 100,000. So these are a change in 100,000 or percent change of glaciers that are at least 100,000 square meters. So between 1966 and 2005, the percent change of these glaciers. So it varies from, let's see, about 7% change or 7% loss to 50% loss of a glacier. And then smaller glaciers, so these glaciers no longer exceed 100,000 square meters. So some of these have lost as much as, 77% of their area. So if you want to go to Glacier National Park, do it now. Okay. How about something else cold? Snow cover. So this is the kind of normal winter maximum extent of snow cover. So actually we have open ocean, we have sea ice that we talked about before, and we have snow cover. So average is about 47 million square kilometers covered by snow in the northern hemisphere. Another way to look at it, again, is this extent. Snow cover in the northern hemisphere between 1980 and 2011 or something. And so snow cover seems to be declining. Area covered by snow cover in the northern hemisphere is declining, and that decline seems to be accelerating. So we're losing snow area covered by snow more rapidly. And here's just another way to look at it, broken up by season. So winter, December, January, February, spring, fall, summer. So what do we see in this graph? Well, we see that in fall and winter, there doesn't really seem to be a change in snow cover, right? But in spring and summer, there has been a decline in the millions of square miles covered by snow. So that suggests that maybe we're getting maybe the same amount of snow in the winter, but it's melting more rapidly in the spring and summer. Now we know that snow is the result of having cold temperatures and water, right? Precipitation. You got to have those to have snow. So here's a way of looking at it. This is 2013, and the snow-covered days different than average. So blue will be more snow than usual. Brown is less snow than usual. So we see that in 2013, there were some areas with record lows of days of snow cover. On the other hand, we also see that there were actually maybe some record highs of days of snow cover. And that's probably because precipitation is more in those areas. So a couple weeks from now, we'll talk about why that might be. The snow cover is changing. how about sea level rise? So that's not really climate, right? It doesn't really seem to be climate, but we'll talk about why sea level might be rising next week. But it's another thing, if we just think right now about global change, not necessarily climate change, but global change, it's something else that is increasing or changing. So if we look back thousands of years ago, sea level rise was actually rising a lot faster than it is now. So in this post-glacial period, sea level rise was actually rising about 1 millimeter per year. Now, it's only 0.1 millimeter per year. Yeah, so. But let's look more closely at our recent past. So again, this is satellite data of sea level, 1993 to present. And again, we can see that recently sea level has been rising at about 3.3 millimeters per year. And here's just another way of looking at it. Change in sea level in inches now. Okay, they didn't use our millimeters. But this is based on tide gauges as well as satellite data. And we can see that sea level is rising. And if we look in the recent past, just the last couple decades, sea level rise seems to be accelerating. Florida, by the way, if you're in Florida, sea level rise is about 20% greater than the global average. A little scary. And this website is really, really cool. So you can go on here, look at your favorite place in the world, and see comparative sea level rise, sea level trends in millimeters per year, which is really cool. And we'll find that some places are actually sea level is decreasing. And we'll talk about why that might be. Okay, extreme weather events are another thing that is changing on a global scale. So this is, I just pulled out a year, 2011, record-breaking weather events. So this includes record rainfall, record snowfall, temperature in some of the same places as the record snowfall, wildfires, extreme drought, extreme flooding. And these are record-breaking. So, this is the first time that place had a temperature that high in 2000, and it happened in 2011. So you can imagine some of the maybe agricultural implications of record temperatures or extreme drought, for example. So my aunt in Washington State said that on Facebook that she can't get canned pumpkin. Their stores are out of canned pumpkin because there was too much rainfall in the Midwest, where most of the pumpkins are grown, a drought in California, where some other pumpkins are grown, and so now, for the second year in a row, we have a pumpkin shortage. So extreme weather events are going to have agricultural and many other implications. Where did my other graph go? I don't know what happened there. So let's see. This is tropical storms. The incidence of tropical storms seems to be increasing. So again, extreme weather events. This NOAA website has another really cool interactive thing that you can do. You can choose different places in the United States. You can choose different extreme things to look at, temperature, precipitation, drought, and it'll build graphs for you and stuff. Kind of cool. So one of the things that we see, so for example, 1910 to present, temperature extremes of high and lows, and this is proportion of the U.S. experiencing extreme highs and lows. So one of the things we see is that record highs seem to be increasing, and the number of record lows seems to be decreasing, again suggesting that temperatures are warming. And in fact, starting in 1996, NOAA, National Oceanographic and Atmospheric Administration, developed what they call the Climate Extremes Index, which takes into account, through some mathematical modeling, monthly maximum temperature, minimum temperature, precipitation, drought severity, and wind velocity of tropical storms and hurricanes. And they munch all this stuff up, and they come up with this CEI, Climate Extreme Index. So they're finding that this Tropical Extreme Index, or the CEI, not tropical climate, is increasing since 1960. So they went back and calculated it for previous years after they developed it in 1996. And if we look more carefully at this, what we see is that there's events that are more extreme than average, and then these would be less extreme than average. But there's getting to be fewer less extreme years than there used to be. Okay, maybe I really am going to get through all this. I'm almost done. Okay, ocean acidification. Not really climate. And I'm not going to talk until next week about why the ocean is acidifying, but it's another global change that we notice is happening. So the ocean between 1875 and 1995 has become more acidic. It's estimated that the ocean, that little ball of water, the little skin of water, has absorbed 2 billion tons of carbon dioxide. And we haven't talked about where that carbon dioxide has come from. Talk about that next week and the following week. But the surface water's acidity has actually increased by 30%. And this is, we can measure this at different places. So we have carbon dioxide levels increasing, and as a result, the acidity is decreasing. And that has implications for organisms like corals and bivalves and phytoplankton and things that need calcium carbonate to make their shells, because they can't do that when the oceans are acidic. So here we have 25%, 30%. Okay, it's increased. So pre-industrial pH was about 8.2. Now it's about 8.1. So that represents, if you know about pH units, that represents about a 25% increase in pH, or in acidity. Okay, so there's a variety of global change events that have been occurring, some over millions of years and some much more recently. But there's a lot of global change happening. So the world is changing. So that's some of the evidence that some of these people would be like, yeah, look, see the climate change. But next week we'll talk about what is actually causing the climate change. So next time we're gonna talk about what alters the system. So what is the Earth's climate system? And what drives the Earth's climate system? All the way from changes in solar input, right? To, let's see, volcanic activity and human influences. So over the next couple of weeks, we'll be talking about drivers of the climate system. And then in week 3, we'll talk about the evidence for human impacts on climate change.